Okay, do we have any questions on, I wonder if we ought to go over some of the worksheet problems. So the first section is talking about valence electrons. Are we good with valence electrons? What the ion would become. No questions? Okay, what about Lewis? Oh, yeah.
Could we just review like valence electrons again?
Yeah, sure can. So if you remember from the periodic table, let's pull up the periodic table. Okay, every element in this first group is going to have one valence electron. And why is that?
Because the electrons are around the first ring in like the Bohr's model.
Good. Perfect. So that's one way to think about it. They are, so if you look at hydrogen has one electron. And, well, it's the one on the outside, so it has one valence electron. Lithium, if you look at the electron configuration, it's 1s2, 2s1, right? On the highest energy level, we have one valence electron. One electron on the highest energy level. That's what definition of valence electron. And so that's lithium. For sodium, it's 1s2, 2s2, 2p6, 3s1. On the highest energy level, we have one electron. Okay? Do you see that? And that's how group 1 will always end in S1.
So the number of valence electrons a element holds, is it the last one or all of them together?
It's the highest energy level. So here, energy level 1, energy level 2, energy level 2, energy level 3. So in energy level 3, that's the only part that we're dealing with, and there's one electron. Does that make sense?
Yes. Well, would the answer be 1?
1.
Okay.
In group 1, all elements in group 1 will have one valence electron. All elements in group 2 will have two valence electrons. All elements in group 3-tene, notice how I called it 3-tene, because there's 3 valence electrons. In group 14, there's 4 valence electrons. In group 5-tene, there's 5 valence electrons. So in all of these, right? And in group 16, there's 6 valence electrons. In group 17, there's 7 valence electrons. In group 18, there's how many?
8 except for helium.
Except for helium, that's right. Helium only has 2 electrons total, so it can't have more than 2 valence electrons. Are we good? Okay. Can we determine the charge of these elements if they're in an ionic compound?
Yeah, that means that like, could you give us an
Yep.
example?
So let's do oxygen. What's the charge for oxygen ion? If it was going to bond with a metal, what's the charge of an oxygen ion? -2, or 2 minus. Okay, so if we look at the the periodic table, it has 6 valence electrons, and how many do all of the elements want to have?
0? 8.
They want 8. They want just the same amount as the nearest, what?
Noble gas.
Perfect. The nearest noble gas. So oxygen, the nearest noble gas is neon, has 10. Well, it starts with 8, or we can say oxygen has 6 valence electrons, neon has 8 valence electrons, so we need 2 more, right? And electrons are positive or negative?
Negative.
They're negative, so we add 2 more negatives, becomes 2 minus, or negative 2. You with me?
Yes.
Okay, what about neon? What's the charge for a neon ion? Trick question.
It's nothing.
Yeah, it's 0. Because it's a noble gas, it's not going to gain or lose any electrons. Good, it already has 8. Are we good with section 1? You guys all have this paper? Okay. What about Lewis structures? Are we good with Lewis structures? Or do you want to do some more? Some more? Okay. Let's see. So we want to try a simple one or a more difficult one? We can do both. Okay. All right, so we have, let's say, H2S. In fact, if you know the steps, if you understand what's going on, they shouldn't be that difficult. Now, some of them, let's see. Yeah, I guess some of them might be difficult, but the ones that I'm going to test you on probably won't be difficult, okay? All right, so what's our first step? Draw the Lewis structure. Go ahead.
Count the valence.
Count the valence electrons. Perfect. And so we just barely went over that. How many valence electrons does hydrogen have? Everybody? 1. And there's 2 hydrogens, so all the hydrogens in our compound, total of 2. You with me? And sulfur it's in group what? 16. So it has 6. So we have a total of 8 valence electrons for this compound. You with me? All right, what's our next step? Determine what atom goes in the center, because we're just going to draw these, right? So which one goes in the center, H or S? Hydrogen or sulfur?
Hydrogen?
Hydrogen is never the central atom. Why not? Let's try it. Let's just try it. So H, and we got S, and we bond the other H with it, right? If that's the central atom, there's a problem already. How many electrons does hydrogen have around it?
1.
2, 4. There's two pairs of electrons around that hydrogen. And each bond is 2 electrons, right? And so, well, can that happen? What is the octet for hydrogen? How many? 2, right? Just like helium. The closest noble gas to hydrogen is helium. It wants to just have 2. That can't happen. So hydrogen will never be the central atom. It can only be bonded to 1 atom. So it's going to be sulfur. How many electrons have we used so far? 4. There's 2 bonds. Each bond is 2. So that's 4 electrons. We have 4 electrons left. Where are we going to put them? Are we ever going to put them around hydrogen? No, hydrogen's done. It only wants 2. We'll put them around the central atom here until we use up all electrons and also until they have an octet. Good? All right. Now we check to make sure they all have an octet. Does this, I didn't mean to do that. Does this hydrogen have an octet? Yeah, it's helium's octet. This hydrogen, same thing. And the sulfur, we got 2, 4, 6, 8. Also has an octet. We used all of them. That's first check. Make sure we use all of the valence electrons. Second check, make sure they all have an octet. We're good? So that's the Lewis structure. Very good. Let's do a more complicated one. CH2O. This time it has 3 elements in it. Does that change how we do it? It doesn't. No difference. Okay, so first thing, we've got to count the valence electrons. How many does carbon have? 4, good. How many does hydrogen have? 2 total, because there's 1, but there's 2 of them, right? How many does oxygen have? 6, that's a total of 12 electrons. Good? All right, essential atom. Now we got 3 to choose from. Is it hydrogen? No, never. So we got carbon or oxygen. This one's hard to tell because there's 1 of each, right? So how do we tell which one the central atom is? The one that is least in what? Go ahead. Electronegativity, right? And if you have this chart on your reference sheet for the midterm, you can just look at it, right? You can take a picture of this, shrink it down, put it on your reference sheet, right? So which one is lowest in electronegativity, carbon or oxygen?
Carbon.
I like to think about it. Which element on the periodic table is the most electronegative? Which one? Out of all of the elements, which one is the highest electronegative? Fluorine is. So whatever one's farthest from fluorine is the least, right? Okay? But if you have this sheet, you could just look at it, right? So carbon is the least electronegative, besides hydrogen, but it's never going to be hydrogen, right? And we're going to bond all other atoms to carbon. And there's 2 hydrogens, and it doesn't matter exactly where you put it, and 1 oxygen. So that's not the only way I can draw this, right? Are we good? Questions so far? All right, how many electrons have we used so far?
6.
6, so we have 6 left. Where do they go?
Around the oxygen and carbon.
Which one first? Oh. Oxygen and carbon. Why oxygen? Real loud? Okay, good. A little bit. Anybody know why oxygen first?
Is it because it has the most electrons?
That's it. What does electronegativity mean? The ability to accept electrons during a chemical reaction, right? So let's give it to them. Let's give it to the most electronegative first, because it wants to take it in more. It's closest to those noble gases. It's going to want to take them in more, right? So we're going to put them around oxygen first, 2, until it has an octet, 4, 6. Oxygen now has an octet. Do we all understand that? Can we all see that oxygen has an octet? Okay. So we don't have any more valence electrons, so we can't put any more. What's our next step? Check. Yeah, check to make sure they all have an octet. Do they all have an octet? No, they don't. Carbon doesn't, so we just keep sharing. So we're going to take, who has extra to share? Oxygen has plenty over here. Uh-oh. I didn't mean to do that. Okay. So we're going to take 2 of those off and make a double bond. Does oxygen still have an octet? That's why it's okay to do that. And now carbon has an octet. Hydrogens have octets. So we're good. That's it. Questions? Yeah.
Could you explain one more time why hydrogen has an octet?
Good. So the octet has to do with what elements on the periodic table? The noble gases. every element wants to have an electron configuration like a noble gas because it's balanced. It takes less energy to be like a noble gas. That's why they want to do it, right? So you take, for each element, in this case hydrogen, what's the closest noble gas to hydrogen? Helium. And helium has how many valence electrons? 2. It only has 2 electrons, period. So it can't have more than that, right? And the electrons near hydrogen here is 2. Each bond is represents 2 electrons, right? So that one has 2, that one has 2, and that's the octet. Carbon has 8 total, and oxygen has 8 total. Now you guys don't have to circle these, I'm just showing you, right? Do we get this? Good question, thanks for asking. Do we have any other questions on that? Yeah, Parker.
Well, I guess it's a different
Well, that's okay.
one. Can we do like charged polyions?
Polyatomic ions? You bet. Which one do you want to do?
NO2 negative or NH4 plus?
Okay, we'll do both. NO2 minus. All right. Same thing. There's 2 differences when you do polyatomic ions. What's the first difference? When we count valence electrons, what does this negative sign mean? It means we have 1 extra electron. If it was negative 2, we have 2 extra electrons. If it's positive 1, that tells us we lost 1 electron because it's positive. Electrons are negative. If we lose them, we become more positive. Does that make sense? So let's count them. We have how many for nitrogen? Everybody? Somebody? One buddy?
3.
5, because it's in group 15, right? How many for oxygen? 6, but there's a total of 2, so that's 12 total. We add them, we have 17. Don't forget to add the 1 for the negative. So remember, if you have an odd number of valence electrons, something's wrong. Okay? Question?
Are we going to be tested on like boron, like Lewis structures? It's usually the like.
BF3 is on the midterm. But if we do it, I think the only thing it's going to ask you is it polar or not? We haven't talked about polarity. We're going to talk about that today. And I'll show you how to tell. And so either way, if we draw BF3 like this is how it is. But if we decide, we should take one of those and make a double bond, it won't change the polarity. Okay? That's the wrong way to draw it. We should draw it without that double bond because boron has just 3 valence electrons like we talked about last time, right? So it shouldn't matter, really, but yeah, for this class anyway. If you want to take organic chemistry, yeah, no. Okay. But if you are going to take organic chemistry, yeah, you'll go in a lot more detail than we're going here. Okay? And if you take chemistry 1110, which is a little bit more than this class, then I still don't think you'll do that. So I think we'll be okay. Good? All right, so let's continue with NO2 minus. What's NO2 minus called? Does anybody know? What?
Nitrous oxide?
Not quite. NO2 minus has a special name, nitrite.
Oh.
This is a polyatomic ion. How do we know? Because it has a charge. So do you all have the list of polyatomic ions I gave you? If you don't have one, I can give one to you, but not right now, but just see me after class. But make sure you have that list on your reference sheet for the midterms so that you don't have to memorize them or memorize them. If you're going to take chemistry 1110 for nurses or in the medical field, you have to memorize them. So if you want to start memorizing them right now, do it. Okay? All right, so what's our next step? Once we count valence, so we have one more for this negative charge. So that's a total of 18 electrons. Are we good? Okay. All right. Central atom. Nitrogen, farthest from fluorine, right? Least electronegative. So we have nitrogen with 2 oxygens. Okay. How many electrons have we used so far? 4. So we have a total of 14 left. Put them around oxygen first, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We have 2 left. The other 2 go around nitrogen. We're doing okay? Understand what I'm doing? Okay. So we used all of them. Do they all have octets? Nitrogen doesn't. So we have to share. Who's going to share? Should we share them from nitrogen? Does that work? No, because nitrogen still doesn't have an octet, and now oxygen has more than an octet, right? So we're not going to do it that way. Let's take some from one of the oxygens and make a double bond there. Does it matter which oxygen? Not for this class. Okay? Again, if you take organic chemistry, we'll talk something about resonance, but we're not going to deal with that in here, so don't worry about it. Okay? Are we done with this one? What do we need, Parker?
Charge.
Yeah, we need a bracket with the charge. And again, on this, it's multiple choice. So if you look at all of your choices and you see one with a charge and a bracket, oh, that should ring a bell. Oh, this is a polyatomic ion. Make sure, do I need this, right? Okay, we good? Any other questions on, did you want to do the positive one? Or are we good?
No, that's okay.
Anything else? Any other Lewis structures?
So we're not gonna be tested on the Lewis structure of BF3?
I don't think so, but if you just know it looks like this, then you'll be good, right?
Oh, okay.
I mean, it has, but yeah, I don't believe so. Okay? And why is it okay that boron doesn't have a octet?
Because it can only
Because
allow 3?
it's an exception. It has 3 valence electrons, and fluorine has 7 valence electrons. That's why it works for the exception. If I had my way about it, I wouldn't teach you exceptions. There's not a lot of exceptions. And so in this class, I mostly want you to know the main rules. Okay? But there are some exceptions. And on the test, there are some of the exceptions on the test. So I will have, so like on the electron configuration, group 6 and group 11, I told you that, right? Was that on the test? Yeah. Okay. All right. Any other questions about Lewis structure before I move on? What about naming and writing chemical formulas for covalent compounds? Let me just give you a few and see if you got this. Um, all right, who can name this one?
Nitrous oxide?
I think you heard that from someone else. Is that how we name covalent compounds? How do we name covalent compounds? What's our first step?
Count the first.
We don't have to count anything. Oh,
Well, I guess like, yeah, if there was multiple, but, cause there's not one.
okay.
It's just a single, so it would just be naming the first compound.
Okay, good.
and Counting the second one, and if there's nothing, then just adding an IDE at the end.
Good. So we're going to use nitrogen. And change the ending to IDE. There's one other thing we got to do. That's the steps for both ionic compounds and covalent compounds. But there's one extra step for covalent. What is it? Use prefixes. We have to use prefixes for both elements unless, what?
Hydrogen.
No, not even hydrogen.
Unless there's one
And-
only singular.
Unless the first one only has one, then we don't use the prefix for that one only. So we don't use mono for the first one. That's it. But since there's only one oxygen, we do use mono. So this is called what?
Nitrogen monoxide.
Nitrogen monoxide. Are we good? Who can tell me what N2O is called? Di-nitrogen monoxide. Yeah. Do we get that? So you need to get these prefixes down. What about N2O4? Anybody, someone different? Someone tell me this one. Dinitrogen tetroxide. Or if you want to call it tetraoxide, that's fine. No problem, because on the test it's multiple choice, so you just, and I'm not going to trick you like that, okay? So dinitrogen tetraoxide is fine. What about K2O? Who can tell me what K2O is called? I'll give you a hint. I'm tricking you.
Potassium dioxide?
Not quite. I tricked you.
Potassium oxide,
Why is it potassium oxide?
because it's with a metal.
Oh, it has a metal in it. What does that tell us?
It's ionic.
It's ionic. Do we use prefixes for ionic compounds? No, never. So make sure you check that. Okay? What's this one called? If you have to look at your periodic table, go ahead. Silicon tetrachloride, right? Change the ending to ID, good. Silicon tetrachloride. What about this one right here? Tell me if you want. Calcium chloride. This one has a metal in it, so it's an ionic compound. We don't need prefixes, right? Calcium chloride. Are we good? Can we name them okay? I meant write the chemical formulas if we have a name, I should say. For example, if this is bromine trifluoride, can you tell me what that is? Bromine trifluoride. Br, bromine is Br. Tri is 3, so it's F, fluoride, fluoride. Change the ending to IDE. Just go backwards, right? BRF3. Are we good? Okay, I'm going to give you one more. Can you tell me that name?
Iron trioxide.
Not quite. It's not iron trioxide.
Isn't it like iron 3 oxide?
Iron 3 oxide. Why is it iron 3 oxide and not iron 2 oxide? Because it has what? We got to find the charge of iron, right? Do we know the charge of oxygen by looking at the periodic table? What is it? 2 minus, right? And how many oxygens are there in this compound? 3 of them. 3 negative 2s, that's a total of negative 6, right? Since all compounds, not all compounds, but all ionic compounds are neutral, this side has to be positive 6. And how many ions are there? 2 of them. So split that positive 6 into 2. That's positive 3, or 3 plus. So that's iron. And we put the charge of iron for, why iron? Why is iron special?
Because it's a metal?
Not because it's a metal, because it's a transition metal. The ones in the middle. Those ones are have multiple charges. So you have to figure it out. You remember doing this, or do you don't remember me teaching this? Raise your hand if you remember me going over this. So I did. Good. Okay. That's okay. We can review it as many times as we need. So for these elements right here, the transition metals, they're variable cations. We have to figure out what their charge is. There's 2 more that also follow that pattern. Tin and lead. Did we talk about these? Are they going to be positive charge, positive 4 or negative 4? Who knows, right? Do they have 4 valence electrons, so they're going to gain 4 or lose 4? These are the metals. This one we're never going to use because it's not very stable in nature. But tin and lead, we know about those metals, right? So these act like noble gases, meaning they could have more than one charge. Are we okay with that? Okay. So since iron's charge is 3, we'll use Roman numeral 3, and then change the ending of the second element to IDE, right? We don't use prefixes because it's an ionic compound. Are we good? All right, so that was a little review from a while ago, even. We still need to know that. Okay, it's going to be on the Unit 2 test and the midterm. So let's review that, study that, practice that. If you need to go back and do the worksheet on ionic compounds, do it. Go back and look at those. They're on Canvas in the modules, and I have the answer key with it. So go back to previous exams, previous stuff, and review it for this midterm coming up. Okay? All right, anything else before we start on today's topic? Well, that was just review, guys. All right. Ready to move on? Okay, today we are going to deal with the geometry of these compounds. You all picked up a page, or if you picked it up over here, that if you know how to read that chart, you should be golden. There's only one problem. You have to have that chart on your reference sheet if you want to use it for the midterm or the final. For the for Unit 2 test, yeah, you could just look at it, right? Use all your notes. But if you want to use it for the midterm or the final, you have to minimize it, shrink it down, and put it on your reference sheet. Good? And I think for the midterm, yeah, I know for the midterm and the final, you will only need the front side of the sheet, not the back side. But it seems like on Unit 2 test, there is the T shape. I don't know why he put that on there, but I think he did. Or it might just be for the practice test. Can't remember. Sometimes the practice tests are harder than the real test. I think they are. So if you got the practice test, you got the test. All right. Should we take a little break? Is it a good time for a break? My sugars are low, so I gotta go clean it up. Take a 5-minute break-ish. Sound good? All right, sorry about that.
That's okay.
Any questions? Okay, let's talk about the geometry. So it's called the Vesper theory, valence shell electron pair repulsion. Okay, so the electron pairs repel each other. Make sense? So, so first thing we need to know are the electron regions, the number of electron regions in our molecule, or in our compound. So for example, if we have water, first step we got to do, in fact, let's in fact, before I do that, let me, so when we're counting the electron regions, if we have a compound, let's say, let's do BF3. No. Let's do the NO2 minus that we just did. That looks like this, right? How many regions, when we look at the electron regions, we're counting them only around the central atom. So around nitrogen, how many regions of electrons are around the central atom nitrogen? Well, let's count them. There's this one here, so that's one. That's a pair. That lone pair is counted as one electron region. How many regions do we have right there? Just one. So double pair, double bond or a triple bond, that counts as just one electron region. What's a region? It's like a space, right? It's the same space. That's why there's only one region there. So around this nitrogen, there are 3 regions. Does that make sense? Do we worry about these guys here? Around oxygen? No, we do not. Just the regions around that central atom. That's the only ones we're dealing with. Are we good? Okay. So, yeah, y'all have that sheet in front of you, right? And rather than going through that whole sheet, I'll just show you how to read it, how to use that to help us find what the geometry is. Is that okay? All right. So let's do some examples. Okay, so let's start simple. H2. In fact, before I do that, let's talk about how do we, steps to determine can't write today. To determine molecular geometry. Step 1. We have to draw the Lewis structure. So we're good with that, right? We can all do that? Okay, second step is we count electron regions around central atom. Okay. And then step 3 is we need to count the number of lone pair of electrons and also the number of bonded atoms. Do you guys understand what a lone pair is?
Like 2 over n?
That's right. This pair right here is a lone pair of electrons because it's all alone. It's not being shared with anybody else. Nitrogen is keeping it for himself, right? And what about how many bonded atoms are around the central atom on this compound here? 1, 2. 2 bonded atoms. Are we good? It's the same element, but that's okay. There's still 2 bonded atoms around that central atom. If we can do those things, then all we have to do is read this chart. So let me pull it up here. Okay, so we had, let me just draw this again. So we have, and it has a bracket and a charge, don't forget that. But to determine the geometry, do we care about the bracket? No, we don't, okay? So here's the bonded atoms, and here's the lone pairs. And what's this right here? Total domain. That means the electron regions. So we either have 1, 2, 3, or 4 on this front page. And that's all I'm going to test you on, really. You have the back side if you, I think it might ask you something on the back side for the practice exam too, or practice test. But anyway. So we have how many lone pairs do we have for this compound? We're only considering the central atom. How many lone pairs do we have? We have 2 electrons, but how many lone pairs? Just 1 lone pair, right? So 1 lone pair. And how many bonded atoms do we have? 2 oxygens are bonded to nitrogen, right? So 2 bonded atoms. So we look down here, we have 2 bonded atoms and 1 lone pair. And do we have 3 regions? 1, 2, 3. That should be our first step, right? Count the regions. Okay? So yeah, there it is. So what does this look like? The electron geometry, and you'll be asked to do that as well. What's determine the electron geometry versus the molecular geometry. And it kind of shows you a picture right here. That's what it looks like. What the heck is this? That's a lone pair of electrons. So these electrons are pushing the other bonds down because they're repelling them. Does that make sense? So it looks something like this, where it pushes these electrons as far apart as they can from each other, which is 120 degrees. Does that make sense? So what's the electron geometry called? Trigonal planar. Why do we call it that? Because it looks like a triangle, and it's all in one plane. It's all on the same plane, like a sheet of paper. There's one plane, right? Can you all see that? All right. So let's start simple, and let's do an example of all of these. Okay. I was just showing you how to read this chart. Do you understand how to read this chart? If we don't, we're going to do practice and practice and practice on this today. All right. So H2. Can you guys draw the Lewis structure for this pretty quickly? Looks like this, right? How many regions are around the central atom? Wait, hydrogen can't be the central atom, can it? Except for in this case, because it's the only atom, right?
So one?
There's only one region, right? Good. So one electron region. How many lone pairs?
One.
Do you see any lone pairs around hydrogen? Lone pairs look like this. 2 dots. Do you see those? 0 lone pairs. You with me? How many bonded atoms? 1 bonded atom. So we go to our, I'm going to erase this. We go to our domains or our regions. There's one region. And there's only one option here. That's it. And it's linear. Does it make sense? This is a linear shape. You got 2 atoms, far apart as they can be, just a straight line. Good? And I was going to have a whole bin of these models to show you, and I left them at school. So
At
We're
high
gonna-
school, so you can't even get them?
I can't get them right now because I'd be late. Yeah, I just left them. It's like, I'll try to bring them next time, but are we good? Okay, let's do another one. CO2. If we draw this, I'm going to quickly draw these so that we don't take the time. Is that okay? Can you guys tell me what shape that is? Remember, you can't just look at the structure and tell me the shape. You have to read the chart. Sometimes they're the same, sometimes they're not. Always read the chart. How many
Linear.
okay, so Charlie's saying it's linear. How many electron regions are there in this compound? Go ahead, give it a shot. 2, right? 1, 2. So there's 2 regions. That means we have two options. How many bonded atoms are there? Two bonded atoms. How many lone pairs around carbon? 0. There it is. Linear for both the electron geometry and the molecular geometry. What's the difference between the electron geometry and the molecular geometry? We didn't talk about this. So for this one right here, we have nitrogen and 2 oxygens. If we just look at the electrons, there's an electron region here, electron region here, electron region there. That's trigonal planar. Looks like a triangle, all in the same plane. Are we good? That's electron geometry. If instead we just look at the bonded atoms, what does that look like? Why don't you read the chart and see? 1 lone pair, 2 bonded atoms, 3 regions. Look at the molecular shape. What's this called?
Triangle.
This is called what? Bent. The electron geometry is called trigonal planar. Right? But if we just look at the molecular shape, we don't care about that. I mean, we do care about it because this pair of electron pushes the other ones down, right? But when we're talking about the shape, we're just looking at the bonded atoms. So it looks like a line that's bent. That's why we call it bent, right? Are we okay with that? Do we get the difference between molecular geometry and electron geometry? Okay. All right, so this is linear both cases. So the electron geometry and the molecular geometry, both linear, right? Any questions so far? Okay, let's do another one. Let's do, in fact, let's take a look at this and see something. If it's 1 or 2 regions, it's always going to be linear. Always. So if you don't want to put this whole sheet on your reference page, minimize it. If it's 1 and 2 regions, it's always going to be linear. Just know that. Okay? Okay, so let's do another one. Let's do BF3. Can anybody tell me what that shape is? The electron geometry?
Bent?
We have 3 fluorines, right? And whether we draw it correctly like this, or sometimes we might say, oh, I'm going to share that and put it right there, right? Does it change the shape? It doesn't. So we're going to be fine there. Okay? That's what I was talking about. So these want to be as far apart as they can be. There's 3 regions. So what's that electron geometry called? Go ahead. Trigonal planar. And what's the molecular geometry? It has 3 bonds still, right? Yeah.
Also trigonal.
Same thing, that's it. We okay? Okay, let's do another one. So if we have SnCl2, I don't like that one. I'm not gonna show that one. Let's see. Let's do that one. SO2. So we got sulfur with 2 oxygens, and it's going to look something like that. What's the electron geometry? Everybody look at your chart. Go ahead.
Linear?
It looks linear. If we just look at the Lewis structure, that's why we can't just look at the Lewis structure. We have to look at this chart or just know it in our brain. It has 3 regions. These want to be as far apart as they can be. If it's 3 regions, what's the electron geometry always going to be? Trigonal planar. You get that? So if you look at this chart, the electron geometry for 3 regions is always going to be trigonal planar. Always. That's what 3 regions is. But the more important shape that we're after is the molecular geometry. That's the main one we got to know. Okay? So what's the molecular geometry for this? Bent. Right? This guy pushed these 2 down, making it bent. We can either make sense of that in our brain, or we can look at this chart. There's 2 bonded atoms and 1 lone pair. It's bent. Don't have to memorize it. If we know how to read this chart, we're golden. Is there a benefit of understanding it in our brain? Yes. There is. Maybe not right now, but when we talk about polarity, it's going to be important, okay? All right, and then let's do O2. O2 looks like this. That linear? It looks like it. Should we base it off of the Lewis structure? No, never. Sometimes we'll be right, most of the time we'll be wrong. So always use this chart or make sense of it in your brain. How many regions are around in this compound? Count them. 1? What's the central atom? Yeah.
What's the central atom?
Yeah.
O.
Yeah, oxygen is, right? Does it matter which one? No, just pick one. How many regions are around this oxygen right here?
3.
1, 2, 3. 3 regions. So what's the electron geometry, guys? Trigonal planar. Good? Then you look at how many lone pairs and how many bonded atoms. And that's only 1 bonded atom, so what's the molecular geometry? Linear. Oh, we would have been right. We would have been right. For the molecular shape anyway, right? You want to take your chances? I wouldn't. All right, are we good with 3 regions? So if it's 1 and 2, it's always going to be linear, both electron geometry and molecular geometry. For 3 regions, the electron geometry is always going to be what? Trigonal planar. And then then the molecular shape depends on how many bonded atoms, lone pairs there are, right? Okay. So now let's go to 4 regions. Let's do CH4. Looks like this as the Lewis structure. We have 4 regions. What's the electron geometry called 4 bonded atoms and 0 lone pairs. In fact, what's the electron region called for all 4 regions? Tetrahedral. Now, I'm going to try drawing to show you what this looks like. The trigonal planar, pretty basic because it's all on the same plane, right? Looks like a triangle. But here's a tetrahedral. This is what tetrahedral looks like. We got carbon, we got a hydrogen straight up, and you need to know how to draw these. So do this with me, or draw this down. So I draw the central atom first, 1 bonded atom going straight up, another bonded atom either going 45 degrees to the right or 45 degrees to the left, doesn't matter. I do it this way. So find a way and stick with it, right? And then I draw a little wedge, a little triangular wedged object here at a 45-degree angle the other direction. And then I draw another wedge, but it's kind of like a dashed wedge. Can you all see a 3-dimensional shape there? We got this one sticking straight up, this one in the same plane, this one coming out of the board. That's why it looks shorter. It's sticking out, pointing out toward us. And this one is sticking in toward the board. Can you see that 3-dimensional shape there? If I shade it, maybe it looks a little bit different. Can you see that's a pyramid? Right? But if there's 4 bonded atoms, this is called tetrahedral. Raise your hand if you can't see that. So I have a picture. Maybe I'll just show you anyway. And I don't know if you can... Uh-oh. Okay. Here it is. I don't know if you can see this or not. Can you see that better? So we got, here's the carbon. We got hydrogen up here, hydrogen over here. This is like our wedge, right? It's coming out in front of us. Do you understand why we draw that as a wedge? Put your hand right in front of your face and put your other hand right out here. Which one appears bigger? The one in front of you, right? Or you look at something close up, you can see a lot of detail. Look at the mountain range, you don't see all the trees. It's just a big blur, right? And that's why we draw this one a little bit dashed, right? Does that make sense why I draw it like that? Now, you don't have to draw it just like me, but you have to understand what it looks like 3-dimensionally. Not for this step, but for polarity. Good? Questions? Okay, let's do another one. NH3 looks like this. This is the Lewis structure. What's the electron geometry called? Tetrahedral. Same thing. For all 4 regions, it's called tetrahedral. Oh, hold on. What was that last one's molecular shape called? If it has 0 lone pairs, it's the same name, guys. If you look at let's look at our chart here real quick. Let me erase some of this stuff. So 1 and 2 is always linear, that doesn't matter. But if there's 3 regions and 0 lone pairs, they're the same name. 4 regions and 0 lone pairs, same name. Are we good? Same shit. Excuse me. All right. So that's tetrahedral. What about the molecular shape for this one? Trigonal pyramid. So this one, if I draw it, looks like this. We're going to draw it exact same way. Why do we call that a pyramid? Because that's what it looks like, right? If we don't worry about the lone pair, if just worry about just the bonded atoms, it looks like a pyramid with a triangular base. Trigonal pyramid. Are we good? And then let's do another one. Let's do H2O. That's what the structure looks like. Is it linear? No. What is it? What's the electron geometry called, guys? Tetrahedral. What about the molecular geometry? Bent. So again, if I draw this, looks something like that. And all we're interested in are these bonded atoms, and it just looks like a bent line, right? Okay. And the last one, Cl2. This is still tetrahedral. Tetrahedral. Because you just take one of them, and there's 1, 2, 3, 4 regions, so it's tetrahedral. But there's only one bonded atom, so what's the molecular shape? Linear. And there's another little pattern we can notice. If it's one bonded atom, it's always linear. Good? Does that make sense in your mind? How you feeling? Good? So if you have this sheet, can you do it? And make sure you find a way to put this sheet on your reference sheet. Because this is one whole big page. If you want to take up one side of your reference sheet, go ahead, but for the... All right. So we have about 40 minutes left, 35 minutes left. Let's take a look at the worksheet. Section 1, you could just look at the electronegativity chart, right? You don't need to memorize those. So, says draw the Lewis structure, determine the electron and molecular geometry, and then redraw it the molecular shape. So you have to practice drawing it this way. And the answer key online Has it drawn for you? You can check it. But let's go over a few of these. Anybody see one on there that looks like, ugh, let's do that one. So I'm on section 2 on this worksheet you picked up today.
Section 2,
Yep. Front side.
it goes from section 1 to section 3.
Section 2 is right there.
I think there might have been like a printer error or something.
Section 1,
Oh,
section
I
2.
There
You're
it
good.
is.
No problem. No. Yeah, go ahead.
We do, see, carbon chloride is,
CCl2O?
yeah.
Perfect. Let's do it. CCl2O. All right. What's our first step to determining the geometries, guys? Yeah, we gotta draw the Lewis structure first, right? So good. Count the valence electrons. Carbon has 4. Chlorine has 7 times 2. That's 14. And oxygen has 6. That's a total of 24 electrons. Questions? I'm going through this quickly because we kind of went over this. If you want me to go slower, you just tell me on this part. We good? All right, so what's our essential atom?
Or
Chlorine or carbon? Which one's closer to the left? Which one's least electronegative? Carbon. And we're going to bond all of the other atoms, and it doesn't matter where we put them. So yours might look a little bit different. That's okay. As long as you have 2 chlorines and 1 oxygen, right? How many electrons have we used? 6. So we have 18 left. Where do they go? Around these guys, yeah? And that's 18. We don't have any more. Do they all have octets? Carbon doesn't. Carbon only has 6. So who's going to share? Yeah, who? Now, in the past it says it doesn't matter, but I also told you something else. Whenever possible, make it symmetrical.
oxygen?
We're going to take it from oxygen. Does everybody understand that? If I draw it differently, you see how it's symmetrical? This is the way it really looks. It doesn't look like this. That's just the Lewis structure. You with me? So you need to get practice and good at drawing it 3-dimensionally. When we talk about polarity, if you cannot draw it 3-dimensionally, it's going to hurt you. Okay? All right. So there's the Lewis structure right here. What's the electron geometry? Trigonal planar, good. Does everybody see that? There's 3 regions, so it's trigonal planar. What about the molecular geometry? Also trigonal planar. Does everybody follow? Because there's 3 bonds, right? And no lone pairs. So sometimes we look at something and it's like, oh, that looks a little icky. But if we know how to do the Lewis structure, it really isn't too bad. Any other questions? Any other ones you want to go over? We can go over all of them if you want to. You just talk to me.
So could we do like F on the first category?
Like, are you talking about section 1?
Yeah, section.
So all that's asking is assign the electronegativity value. So if we look at our
Oh,
value chart,
so it's-
it's 4,
Oh, okay.
right? So you could just easily look that up, right? Any questions on section 2? Any others that look a little, ugh?
So section 3, we haven't gone over polar and monopolar.
That's right. That's why we're still on section 2. Yep. If you guys are ready to move on to polarity, we can. How we feeling?
Do you think we have-
Whether we do the practice here, you guys should do this practice. Get it down, okay?
Would we
The
have
key is on Canvas. Sorry.
would we have the time seeing as it's 6:55? Just about?
We can get it started and finish it next time. Yeah. So we're not behind anymore. So we don't have to push it. I'm going a little bit out of order. We already talked about covalent bonding or chemical covalent bonding nomenclature already, which is the last section, 2.4. So you're welcome to do the homework on that. So all we have to deal with now for this unit is polarity and intermolecular forces. So if we get started on polarity, finish the idea of polarity, and then talk about polar molecules next time, along with intermolecular forces, we'll still be ahead. Or do you guys feel like, hey, that might be enough for today? Let our brains, but then you got to go home and practice this. Because if you don't practice this within 24 hours, you're going to forget it. It's like, oh, I thought I would know, but I don't. You guys ever do that? Tell me, what do you want? Who wants to talk a little bit about polarity, just so you have an idea of what it is? Who wants to go home right now because your brains are full? Okay, a little bit more people are saying let's go home. Okay, I'm going to read you guys, and I've pushed you real fast this semester so far, and that's my fault because I took a day off. So, yeah, let's just call it a day. Do you have any other questions on this? Okay, go home and practice them. The answers are on Canvas. And then we'll finish, talk about polarity next time, and maybe that's it. Next time we'll just talk about polarity. And the following time we'll talk about intermolecular forces. Sound good? And then we'll be done with this section, ready for the midterm. You guys getting ready for that midterm? Getting your reference sheet all made up? Because on the midterm, you only get one sheet double-sided.
When are we taking the midterm?
Let's see. So next time we'll do polarity. The 18th we'll do intermolecular forces. So we could do a review on the 20th, and then the midterm, or no, yeah, we'll do a review on the 20th, and then your Unit 2 test is going to be that weekend-ish. And then we can do the midterm on the 25th or the 27th. I'll give you a choice. But if we do it the 27th, we're going to start the next unit on the 25th. What would you guys rather? Who says midterm on the 25th? That's a Tuesday. Who said midterm on the Thursday after that? Okay. And most of you don't care.
Maybe.
We'll see. We'll see how it goes. We'll play it by ear.
Maybe we could do a revote when we get a little bit closer to it.
Sounds good. Good idea. All right, ladies and gents, have a good day. Take care. Thanks.